Okay, well, thanks for tuning in. I just wanted to offer this as kind of a supplement to the handout that you're working on today. So, if you, what I'm going to focus mainly on the first three questions. Okay, just to kind of clarify a few things. So, in the beginning, we're focusing on this one compound that we call potassium nitrate. Okay, and I just want to kind of take it apart a little bit and show you what are the component parts of a unit of potassium nitrate. Okay, so sort of, in symbolic language, if I want to represent this symbolically, I would use the element symbols, right? So K for potassium, NO3 is nitrate, and then when you put those together to form the whole compound, potassium nitrate, then you use, you put the K and the NO3 together, okay? Now, sort of in a picture form, the potassium ion is this, it's a single atom, and it has a single plus charge, right? And if you look on the periodic table, potassium has 19 protons, and so in order to have a net charge of +1, you know that it's it's lost an electron and it only has 18 electrons. This is what one way you can represent the nitrate anion. Okay, so this is the nitrate ion in sort of symbolic language, like you'd use in a chemical reaction. This is one way you could depict nitrate, and you can see, just like the formula says, there's one nitrogen, and then there are 3 oxygen atoms. Okay, now you don't have to worry about the way the oxygens are bonded to the nitrogen. You can see that 2 of the oxygens are connected to the central nitrogen with single bonds, and then this guy here is connected with a double bond. Don't worry about that. That is way ahead of where we are right now. All I want to convey is that the nitrate anion is just this, think of it as a unit. Okay, down here I kind of made the analogy with a tricycle, right? So that's all you got to know. Now then, I'm using a couple of other terms that I want to clarify. I'm using the terms monatomic ion to characterize the potassium, and I'm using the term polyatomic to characterize the nitrate. And so let me just let me see if I can do this. Let me, oops. 1 second. I'll get there eventually. Maybe. Okay, here we go. Sorry about that. Okay, so monatomic, so the word monatomic comes from monoatomic, which simply means one atom, okay? And so here are 2 examples. One example of a monatomic cation, and one example of a monatomic anion, okay? So they're called monatomic because the ion is comprised of just one atom. Now, polyatomic, okay, that's the word we use, is used to refer to ions where there are more than one atom. Okay, so poly means many, more than one atom. So here you've got 4 hydrogens, 1 nitrogen. Here's our friend, the nitrate. Okay, so this would be cation, this would be a polyatomic anion. And as I mentioned, in the last slide, the nitrate, if you kind of open it up and look at the way the atoms are connected, this is one way you can think of it, okay? And we think of it as a unit. Okay, so what I'd like you to do now is I want you to look at each of these 6 ions, okay? And I just want you to write them down on your paper. So let's go, so in the space below paragraph number 1, I'd like you to simply write, copy these down and then label them as either monatomic cation, monatomic anion, polyatomic cation, or polyatomic anion. Okay, so go right ahead. Okay, so hopefully you've got all 6 written down, and let's go over the answers. So this is the chloride, and it is a monatomic anion. monatomic anion. This SO3 2-, clearly there's more than one atom, so it's polyatomic. It's got a negative charge, so it's a polyatomic anion. Here we go. This is a single atom, and it's positively charged, so monatomic cation. Monatomic cation again for the aluminum, 3+. For the PO43-, this is polyatomic anion, and this is monatomic anion. Okay, so hopefully that wasn't too bad. Now, let's go back to here. Now, in paragraph number 2, I talk about how cations and anions can come together and form ionic compounds. Okay, and when they do that, they are almost always solids. And in the solid form, these ions, they arrange themselves in what you might call arrays, or sometimes they're called lattice structures. And they, because of the charges, they like to arrange themselves into a pattern of alternating positive and negative charges. All right, so let's see what we mean by that. So let's say I've got a whole bunch of potassium cations and a whole bunch of nitrate anions, and I want to like put them together to make a compound. Okay, so if I start with one potassium cation, then what would I want to put right next to it? And don't forget, you have to remember the rules about charges, positive and negative charges. So this, for example, would not be the way you want to do it, right? You don't want two positively charged ions next to each other, because we know that like charges repel. So I think a better idea would be to put the nitrate right next to the potassium, and then follow that with a potassium, okay? And then let's say we want to start another row here. Well, then you'd want to put the nitrate right underneath the potassium, tuck a potassium in here, and so on. Okay, and so you would do this not only in up and down and side to side, but you would also do this in a depth kind of way to make a three-dimensional solid. Okay, so again, this is the most stable arrangement, because if you're potassium, when you look around, you want your nearest neighbors to have negative charges, right? Because opposite charges attract, and that makes for the most stable compound. Okay, and then this is another way to depict the structure of an ionic compound that's made of cations and anions. So here, if this were the way we wanted to represent a crystal of potassium nitrate, then you could think of the little purple ions as being the potassiums and the green ones being the nitrates, and you can see it makes this checkerboard pattern of alternating positive and negative charge. Okay, let's go. So that's that. And then the last question here is, based on the chemical formula for potassium nitrate, what do you think is the ratio between the potassium and the nitrate? And you can see from the formula that for every one ion of potassium, you have one nitrate. So there's a 1-to-1 ratio here, okay? And you can get that from the formula. So for example, let's look at sodium chloride, okay? So you have, in the formula, it shows one atom of sodium, one atom of chlorine. And so the ratio here would simply be 1-to-1, right? So if you were writing this, it would be 1:1. Now let's take a look at this compound. This compound is called calcium chloride. And here you can see that for every one atom of calcium, we have 2 atoms of chlorine, I should say. And so the ratio here would be 1:2, a 1-to-2 ratio. So now take a second and see if you can write down the ratios for these next 3 compounds. Okay, and when I ask questions like this on these videos, you should always pause and then think about it, and then I'll go through the answer with you. So here it looks like there is there's one aluminum, and then here you see the NO3. This is a nitrate. all right, just like we were talking about earlier. And we think of it as one unit, a self-contained unit. But because you have parentheses and a 3 out here, that means that there are 3 units of nitrate. So the aluminum nitrate ratio is 1 to 3. 1 to 3. Here, now we've got a SO4, which is a polyatomic ion, and SO4 is a unit, and we have 3 of them. Over here we have 2 aluminums, so you can see that the ratio between aluminum and sulfate is 2 to 3. And then here we have a polyatomic cation, the NH4+. We have 2 units of that, 1 unit of the CO3, and so this is a 2 to 1 ratio. Sorry, so 2 to 1 ratio. Okay? All right. Now, going down, item number 3 here is just talking about the behavior of a lot of ionic compounds in water, and it turns out that a lot of these ionic compounds are pretty soluble in water. Okay, so just to kind of show you, so just imagine that we've taken our lattice of potassium nitrate, and we've dropped it into water. Okay, so that's what this blue background represents. We're immersed in water, and so when it dissolves, basically the ions just kind of separate from each other. So the individual ions detach from the main structure, and they just go floating off, and they're surrounded by water molecules. Okay. Now the other thing that happens, it says here, and the resulting solution would conduct electricity easily. So what I would like you to do in the space beneath number 3 is I'd like you to draw a, here I'll show you. Imagine that we have 2 electrodes that have been dropped into this solution of potassium nitrate, and we're going to attach these electrodes to some sort of a voltage source, a battery. And so this electrode is negatively charged, this one's positively charged, and so over here in the space, if you could just kind of draw the negative electrode on this side, the positive electrode on this side, and just sort of draw a couple of potassium ions, draw a couple of nitrate ions, and show with arrows the direction that each ion would feel pulled. What direction would it be pulled toward? Okay, so in animated form, hopefully this is kind of what you sort of what you depicted on your paper. So positively charged ions are going to feel a force toward the negative electrode because opposites attract, and the converse is true with the nitrates and the positive charge, positive electrode. Okay, and finally, just to kind of get you guys going, I think you guys were okay with these questions. I had a lot of people say, am I missing something? This seems too easy. But just wanted to make it clear that if, every pair of potassium and nitrate would be considered a unit, 1 unit of potassium nitrate. So if we have 10 units of potassium nitrate, then we would have 10 potassiums and 10 nitrates, right? If we had 1 million of those units, we would have 1 million potassiums and 1 million nitrates. And then if we take this, if we scale it up even more, and we said, hey, let's say we have 1 mole of potassium nitrate, which is this big number, then you would have Avogadro's number of potassiums and Avogadro's number of nitrates. You can think of it just like, saying 1 dozen of, that means 12. Well, 1 mole equals 6.022 times 10 to the 23rd. Okay, cool. Now, here's the next compound that's talked about in your handout. You can see it is, it's this big structure, and so let me try to break this down a little bit. So the main structure is sodium sulfate. Okay, so here's the new formula up here, and you can see that it's made up of sodium cations and sulfate anions. The sulfate is 1 sulfur and 4 oxygens, and you can see that here. Okay, and again, you don't need to know, this structure. You don't memorize that. What I want you to know, though, is that the SO4, whenever you see the SO4, consider it to be like an intact unit. All right, you don't break it apart or anything like that. It just kind of is a self-contained unit. And the sulfate anion happens to have a 2- charge. Okay, now sodium is only single plus, and so if we want to have a neutral compound, a neutral unit of sodium sulfate, you've got to have 2 sodiums, right? So the sodiums have to double team the sulfate in order to neutralize that charge. Okay, so here's what the symbolic representation or the formula representation. This is a picture form, and hopefully that makes it a little bit clear. Now, we're just about ready in lab in the next couple days to study these complexes, and so here is a kind of a fictitious complex that I'm using to illustrate the concept of a complex. So here we're going to imagine that 1 unit of sodium sulfate complexes with 3. We're going to call these carbonates. Okay, so here's 1, here's 2, here's 3, and okay, so that's the name, and so we could represent that in a formula as this. We would just put a little dot here between the sodium sulfate, and then we would put a big 3 to indicate that there are 3 units of carbonate, and then here's the formula for carbonate. Okay, now that's, I guess, really all there is to it here. And then there's some questions here that will lead you step by step. I'll just talk about 7a here, just to kind of, confirm what you hopefully are thinking. So if we had 10 units of sodium sulfate tricarbonate, okay, so that's this thing right here, sodium sulfate tricarbonate, then we would have 2 times 10 sodiums, right? Because if every unit comes with 2 atoms of sodium, then if you have 10 units, then you're going to have 10 times 2 sodiums. All right, so you've got 20 sodium atoms. Each unit of this stuff comes with 1 unit of sulfate, and so you'd have 10 units of sulfate. And then because each unit comes with 3 of the carbonates, if you have 10 units altogether, that'd be 10 times 3, that'd be 30. So you'd have 30, carbonate or carbon dioxide units. Okay, so that's as much as I'll say. We'll take it up there the next class, and thanks again for tuning in. See ya.